Good morning. Okay, let's get this going here and then we can get started. I am, oh, hi, buddy. You want to come up here? Okay. I have got, Oz with me. Okay, cool. So today, we're going to start, chapter 3. I just want to do a couple of examples, though, of dealing with acids. First, we talked about how to name them last time. I want to go from then the name to the formula. I just want to do a couple of examples like that, and then we'll start chapter 3. So cool. Let's get started. So I'm in a different room today. I'm in one of the closets actually with a old laptop streaming because I'm moving today and this week. So totally crazy. So if last time the mic had gotten disconnected or something, and apparently I was silent for like 5 minutes, so if something like that happens again, just let me know. Hopefully sooner rather than later, just because this computer can be a little wonky. So, but we can go ahead and do a couple of examples here. Okay, let's see. Hydro. What shall we do? All right. So, when we're looking at acid names, we already have the name. We're trying to come up with the formula. What we want to do is just kind of like what we did before. We would analyze the name, right? We're going to say, okay, well, this acid ends with us acid. And if we remember what that meant that our original ion was chlorite, right? We had the ite ending that led to us acid. And so then we're going to need to remember that chlorite is ClO2 minus. So very important that we keep that together there. Let's see. Cool. So with that, we've got H plus as our other side, right? That's the acid part. We always have to have H plus. And so to charge balance these, we just stick them together because they have the same charge. And then the last thing we need to do is throw on that aqueous bit there, just to make sure that we understand that this is in water. So, because remember, acids have to be dissolved in water. Cool. With hydrophosphoric acid, we have to consider, okay, hydroic acid meant that something came from ide, right? So this must have come from phosphide, ide, right? This came from ite. The us acid comes from ite. Hydroblankic acid is ide, IDE. And so we have to think, okay, what the heck is phosphide? Well, phosphide, remember, ide ending typically means a monoatomic ion. There are a few polyatomics that are ides, but something like this, we're going to see, would be the phosphide ion. So phosphorus with its preferred charge, which would be -3. We know we have to put this with H plus because it's an acid. So if we combine these, we can crisscross. We get H3P, AQ. Probably not a really good acid, but there it is anyway, so just in case. So, cool. So with that, that's kind of how we can go from name to acid. So you want to analyze the kind of acid naming parts of it. So us acid, ic acid, or hydroic acid. And then you'll figure out what anion that comes from. And then with that, you'll just charge balance it with enough H plus to make it work. And then tack on an AQ at the end. So that's kind of the last bit there. So we'll keep going. Okay, so let's go ahead and start chapter 3. So chapter 3, we're starting talking about chemical reactions. And so chemical reactions, we're finally going to get to some chemistry here. We have a couple of things to talk about. We have a whole lot of information that can be given to us about a chemical reaction. But all chemical reactions kind of follow this pattern. And the barking begins. Miss Jersey, relax. You're okay. I've got like 3 of them in here with me. They're like, what's going on? Why are we in here? So, chemical reactions generally follow the idea where you're taking some reactant or reactants, plural, either singular or plural, and converting them into some product or products. So, there's not really a limit to how many reactants or how many products you're going to have for a reaction. It just depends on what you're reacting. Okay, so pretty cool. We're going to see that an example reaction would be something like this. This one will have nitrogen and hydrogen as our reactants, and we'll have our products, or in this case a single product, be ammonia there. And so these two are just kind of combining and making this. We'll see this type of reaction in a bit. And so we'll go from there. So we would say, again, these guys... Oh, that's the ugliest bracket I've ever drawn. There we go. These are our reactants. This is our product. And so we're going to learn a lot of things to work with chemical reactions like this. We're going to include states of matter. We're going to include the number of each molecule or atom that's reacting. We're going to include potentially some energy associated with reactions. We know some reactions can be explosive. They give off a lot of energy. And so we're going to have a lot of things we can talk about with these. We're going to learn in this and the next chapter kind of how to predict the products of a reaction, how to predict the state of matter of a product, and kind of then finally we're going to deal with how to use a chemical reaction in terms of quantifying. So that means, if we have this much of our reactants, how much product can we get out? That sort of thing. So we're going to see, I'm going to make analogies throughout this to cooking. Our chemical reactions are essentially recipes. And we're going to learn how to perfect those recipes and then how to use them to actually make things. So let's start talking off about balancing reactions. So I hope I said this in the first day, but remember that matter cannot be created or destroyed. We can only transform it. And what this means for us is that the number of atoms of each element must be the same on each side of the reaction. Of your reaction. Reaction is very commonly abbreviated RXN. So there we go. So if we take a look at this reaction that I've given us, we have N2 plus H2 turns into ammonia. What we need to keep in mind is we can't mess with these compounds. We can't just say, well, let's make this easy and let's just change this to N plus H3 turns into NH3. Wouldn't that be nice? No. Unfortunately, we cannot change the compounds here. Once we predict the correct compounds, we're going to see we cannot change those. All right, give me a second. I'm going to just let him out so he stops barking, so he doesn't keep distracting us. In the meantime, try and see if you can't figure out a way to make this work, but I'll be right back. Get out of here. Oh. Okay. he's out there. Now Jersey's gonna bark. Oh well, it'll be a fun couple of days for all of us, I'm sure. So, if we want to look at this, one way to kind of work with this sort of thing is to just kind of keep a tally of how many of each element you have on one side. So we have our reactant side. We've got our product side. With this reaction, we only have two elements that we're dealing with. We have nitrogen and hydrogen. And so we can kind of just keep a running tally of how many we have. On the reactant side, we have two nitrogen atoms. On the product side, we have one nitrogen atom. On the left side, the reactant side, we have two hydrogens. And on the product side, we have three hydrogens. Just to clarify, this is not something you can ever do. So, let me... There we go. So, ignore that one. That's a very bad reaction, a naughty reaction. So, in a chemical reaction, we can't change our compounds. They are already given to us. We have named them. We've done all our fun stuff. We can't just throw those aside now. And so, we're going to have to, instead... How this is going to work is instead of changing our compounds, we can add more of the same compound. If we just look at the difference in nitrogen here, on our reactant side, we have two nitrogens. On the product side, we have one. We have to have the same number on both sides of a chemical reaction because matter cannot be created or destroyed. We cannot destroy or create nitrogen atoms. So, what we're going to need to do is we need this to be 2. Right? We need this to equal the nitrogen side. And how we do that is we're going to add another ammonia molecule. We can only change the number of the molecules we have. And so if we add a second ammonia molecule, how we describe that is like so. We'll say now we have 2 ammonias. And now we'll have 2 nitrogens on our product side. However, doing that has now changed the number of hydrogens that we have as well, because they're both part of that compound. Totally okay. We'll see that. We'll just have to fix that. So nitrogen is balanced. Let's look at hydrogen now. We see, okay, well, there's 2 on the left, 6 on the right. If they all come as pairs, well, I could make 6 if I wanted to by having now 3 hydrogen molecules. Right? And that'll give us 6 hydrogens. And if we go ahead and check everything out, we see, okay, now we do have 2 nitrogens on each side, 6 hydrogens on each side. We are balanced. So we will have kind of completed our reaction. So hopefully not too bad. Let's do another one. In this case, we have 1 reactant going to 2 products. Again, totally okay. We can have as many or as, we have to have at least 1, right? But at least 1 reactant, at least 1 product for all reactions. So if we want to balance this, we'll say, okay, we've got our reactant and product side. We've got hydrogen and we've got oxygen. Those are the 2 elements that we have here. If we look at hydrogen, we've got 2 on the left, 2 on the right. With oxygen, we have 2 on the left, 3 on the right, right? We have 1 from water, 1 from oxygen, O2. Put those together, that's 3, right? So we have to include all of the oxygens on the right side. Well, looks like hydrogen is already balanced, so we can skip it for now. But if we look at the oxygen, we have too few on the left, right? We need to have an extra one. But they come in multiples of 2 in this compound, right? So what we can try to do is do the least common multiple between them. If we have 3 on the right, 2 on the left, let's try to make both of them 6. That's usually a good way to go because, I don't know, we'll try it. If we want to make this 6, then we're going to need 3 of those. Right? Because each one has 2. If we want it to be 6, so that we'll have something on the right for that to go into, we can try this out. We're going to see a lot of balancing is kind of guessing and checking. And so with this, we can see, okay, well now we've also changed hydrogen to 6. So we should probably fix that. If we need hydrogen to be 6, we're going to need a 3 there as well. And that now puts us at 5 oxygens. Oops, that looks like that's not quite enough. So let's try something else. If we want to think here, okay, well really we need just, if we want to think about it this way, let me just put my O2 a little bit more. We have 3 oxygens from the waters now, right? And we have 2 from the oxygen gas, the O2. If we need 5 oxygen or 6 oxygens total, we have 5. Some people like to do this, some people don't. What we could say is, we can say, well, we've got really 1.5 oxygen molecules. And that might be horrible to some people. And it's okay. You can technically have this as long as you fix it later. We're looking at the ratios here. So we want to kind of always look at things as the lowest possible ratio. If you don't like this, though, you can say, okay, well, I'm going to try a different number. I'm going to try and get 5 and 6 to go into the same thing. So maybe I'll try 30. And we'll try going it from it that way. And you can try that. You can go crazy. Have fun with it. If we do this 1.5 business, though, that'll take us to 6. And then we can see, wait a second. All of these, 3, 3, and 1.5, are all divisible by 1.5, right? We can make these into integers. We're looking at ratios between these things. And so if we do that, we can say, okay, well, let's divide all of these by 1/2. If I do that, 1.5, I'm sorry. This becomes 1. This becomes 2. This becomes 2. Just divided all of these. Divided all these coefficients by 1.5. Again, because we want them to always be kind of the lowest ratio that we have. And we can see here, okay, well, that should work, but let's go ahead and check our atoms here. We can say, okay, hydrogen, now we have 4. We have 2 hydrogen peroxides, and we've got 2 waters, so therefore 4 of those. If we go ahead and look at the the oxygens, we see we're going to have 4 now of those. And indeed, we're going to have 4 oxygens. We have 2 from water, 2 from oxygen. And so putting those together, we'll have 4. And so everything will be balanced here. So some of this is a process. Sometimes you guess and check. And so it's just kind of a matter of doing whatever you can. If you decided, I'm going to go for 30 oxygens on both sides, you can totally do that. Go for it. Put your 15 as your H2O2. You'll get 15 waters, and then you'll get 10... you'll get 7.5 oxygens or something. It'll just take more time. So, believe it or not, it's just easier to say these half coefficients here and then just deal with them later. In this case, we were able to divide them all by 1.5. Sometimes you'll need to just multiply things by 2. Whatever you need to do to make them all the lowest possible coefficients. So, that's another one. Let's do some more. Let's do some more balancing. And on Canvas, there is a whole bunch of practice for these. All right, here's another reaction. The way to really learn this is just practicing. There's no kind of easy way to do it. I mean, yeah, there's no like one way that's going to work and it's going to be perfect. So, easiest thing to do, make your list and just make sure that you're got the same number on each side. Do whatever you need to do to get there. Generally, rule of thumb, you'll want to work on the most complicated element last. Very often that will be oxygen, especially if you have O2 somewhere in your reaction. O2 is going to be a pain in our booties. So, cool. Let's go ahead and start this one out. If we look at carbons, we have 3 on the left, 1 on the right. With hydrogens, we have 8 on the left, 2 on the right. With oxygens, we have 2 on the left, 3 on the right. 2 from CO2, 1 from water. Start by balancing out the carbons. Okay, so we need this guy to be 3, so that things are balanced. You can go ahead and put that. So you get 3 carbon dioxides. Now we have to reevaluate our waters, or I'm sorry, our oxygens. We have now 6 from CO2 and 1 from water. That's a total of 7. All right, we've changed something that has oxygen, so we need to change our tallies. Great. Carbon's done. Let's look at hydrogen. We have 8 on the left, 2 on the right. So we need this to be 8. So we'll multiply the water by 4. Each water has 2, so we can multiply it by 4. And now we can go ahead and change our oxygens again. We have 6 from CO2, 4 from water. That is 10 oxygens. And if we go ahead and we can make this one 10 by sticking a 5 in front of the oxygen there. And everything will be nicely balanced. So sometimes things work really nicely like this. You just move down the line, keep track of all your elements, and you can balance it. Sometimes, though, you will need those pesky fractions. If we try another one. Another combustion reaction. Oops, why did I put 3? Just copied the same thing. If we're balancing something like this, process is the same. The process is the same here. Let's say, okay, we've got 4 carbons, 1 carbon, 10 hydrogens, 2 hydrogens, 2 oxygens, 3 oxygens. So do we all see, by the way, like, is this part okay? We're all cool tabulating from our basic reaction how many of each we have? Hopefully not too bad. All right. So let's go ahead and start working on it. So we're going to need 4 here. No. Okay, let's step back then. So Michaela, it's not super clear how we got these numbers. So we can go over that. So with this, if we're looking at carbons on this set of reactants and products, we want to count how many of each that we have. So if we're looking at the reactant side, that's the left side, which has R. Sorry, I don't make that up. We have 4 carbons to start, right? C4H10 is our only carbon-containing compound on the reactant side. There are 4 carbons in that molecule. On the right side, the only thing that has carbon is CO2, and there's just 1 carbon in CO2. So that's how I got those. For hydrogen, I did much the same. I saw there were 10 hydrogens on the left, 2 on the right, looking at the butane versus the water. You don't need to learn how to name butane, though, but that molecule is butane. And then on the left, I have 2 oxygens from oxygen. The only part that might be complicated is this 3 is, it's 2 oxygens there and 1 oxygen from water. So that's where that 3 comes from. So it's just a matter of keeping track of them all. So that's where I got those numbers. I'm going to go ahead and erase these arrows, though, just so we have more room. But that's where all those come from. Cool. So if I need my to have 4 carbons then on my product side, because I want them to always be equal, if I need 4 on this side, that means I need to multiply our carbon-containing compound by 4, right? And doing so, I will now have 4 carbons. But by doing that, I've also now added more oxygens. I now have, I've got now 4 times 2 plus 1 from the water. So again, 4 times 2 now, 1 from the water. And so that'll be 9 altogether that we've got for oxygen. All right. So just keeping track of things as we go. Right, so next thing to balance is hydrogen. On the left, I've got 10. On the right, I've got 2. So what I need to do there is multiply our water by 5, right? Because 10 times 2 will, 2 times 5 will give us 10. So we'll need to multiply this by 5. And so we'll need to now adjust our calculation. We need to do 4 times 2 plus 5, which gives us 13 now. So always, keeping track of everything. So oxygen is always the pain. And so again, we could try now putting 26 for our oxygen, because 2 and 13 don't, I can't just, multiply one of them to get 13, though I can. If I wanted 13 oxygens on the left side, but my only thing comes as a pair, if I need 13 oxygen atoms, but they all come as pairs, again, we can just say 13 over 2. That'll get us to 13 oxygen molecules. Or 13 oxygen atoms, rather, that we need on both sides of the reaction. I'm telling you now, it's the easiest thing to do if you can just put it as a fraction. If you have an odd number of oxygens, and you have O2, just put your odd number of oxygens divided by 2 as your coefficient. And that'll bring us to 13. Because 13 over 2 times 2 is 13. Yes? So that'll give us 13 if we do that. And so, since we, though, don't want fractions in our answer, and none of these are all divisible by the same thing, like they were in a couple of problems ago, these were all divisible by 1.5, we don't have such luxury this time. We have 1, 13 over 2, 4, and 5. None of those are divisible by the same number, except for 1, but who cares about that? So what we'll want to do, in order to get them to integers, to get rid of the fraction this time, is we'll multiply everything by 2. And that will get rid of our fraction there. And by doing so, we end up with, I'm going to erase this math here, we end up with 2 butanes plus 13 oxygens turns into 8 CO2s plus 10 H2Os. Multiply everything by 2, cancels out our fraction, and we're going to be left with whole numbers. And if you wanted to instead say, okay, well, 2 and 13, let's try making those equal to 26. You're going to get the same answer if you didn't put the 13 over 2. If you decided instead, okay, I'm going to make both of those equal to 26. That means I need 13 oxygens there. You're going to have kind of a pain working with the 13 on the right, though. So, again, fractions are going to be our kind of easiest way to deal with diatomic molecules like oxygen, where they come as pairs. It's just easiest to put them as fractions. Sometimes we don't have to worry about fractions. We got them to nicely equal 5 here. We didn't have any fractions. But in this case, we did need fractions. And so what we just need to do at the end is cancel that fraction out somehow. Multiply or divide by something that's going to get rid of our fraction. Oftentimes that will be 2. All right. So this is a skill that, you may not be super confident on right now, but practice, practice, practice. That's going to be our friend here. There is plenty of balancing practice on Canvas. If you are on our homepage, you scroll down to the module called Extra Practice. I know, Oz. Can I put you down, buddy? If you look in that module, you'll see there is... maybe I should just try and find it. Okay, give me a sec while I go on to Canvas here, and I'll show you guys. cerocoso.edu. So, we're going to see that there's plenty of practice, hundreds of problems for you to practice on, assuming my links still work. Where the heck is Canvas on this page? Oh, it's probably inside CC. Okay. Sorry, I'm using this old laptop that doesn't have any of my things saved, so it's okay, there we go. All right, Canvas. I just want to show you exactly what we're looking at here. So, okay, Canvas, there we go. Okay, I'm going to show this part of the screen. So if I do that, hopefully this will work. Yes, cool. Okay, so on Canvas here, it should be the same on both of those. I've got grading to do, hooray. We don't need to look at all this stuff. If we scroll all the way down to extra practice, we'll see here we have balancing equations. So we can click that. Again, we're probably going to have to click this, and oh shoot, it's not working. So that's unfortunate. I will try and find you a link to this. This one was really nice because it had hundreds of problems where you could practice your own thing. So we'll deal with this. I'll find you another link for balancing equations. So that was all for naught. Okay, and now I'm back on Twitch, watching myself stream Twitch. Never mind. Okay, but suffice it to say, I'm going to find you as a practice now that link doesn't work anymore. And so you'll have plenty of practice to do. And it's going to be kind of a check your own sort of thing where you'll be given an equation and you'll be able to choose or input numbers for your coefficients, and then you can check your answer. And it'll tell you whether you're right or wrong. And so you can do that. And that'll be useful. Okay, so with those, so what will be on Canvas, and that may take me a day or two to fix because with the moving, the schedule is completely ruined right now. So I have to work with the movers as soon as class is over today. But we'll get that eventually fixed. Cool. Though we're going to have a lot to talk about with these. We're going to talk about a couple of reaction types. Next, so we're going to learn kind of how to predict the products of reactions. Actually, I've already given us the 3 types that are covered in this chapter. Our first kind of reaction type is called synthesis or combination. And this one generally follows the form of 2 things turning into a third thing. So that might be written like this. And with this, I had given us this equation, right? This is a synthesis reaction, a combination reaction. We're taking two things and putting them together to make a third thing. It's a pretty simple type. Yeah, it looks like it did the same for me. So we'll fix that. Don't you worry. Later on, maybe today, maybe later today, maybe tomorrow, I'll fix that. I'll find the link, what happened to it, and we'll repair that. So don't worry, we'll get there. But anyways, so with regards to reaction types, though, this is kind of one of our easiest ones to observe. For our purposes, though, I would like us to be able to predict their products. Sometimes that'll be easy. Sometimes not. You should be able to, though. We're going to see predict the product of a metal plus a non-metal reacting. So for example, I want to maybe give you something like this. You should be able to predict the product of this reaction. So we've learned now, last week, we talked about making ionic compounds, right? We learned about their preferred charges, and we learned how to balance those. So you should be able to, therefore, take elements and put them together, if they're a metal and a non-metal, into the correct compound. So for this one, you should get an ACl, right? We know that sodium will take the charge of +1, chlorine will take the charge of -1, and that's how that'll work. If you want to balance this, by the way, that's what you would need to balance it, but hopefully not too hard to see that, right? This sort of reaction I would expect you to be able to come up with a product for. If I gave you calcium and nitrogen, you should be able to say, okay, well, calcium I know takes +2. Nitrogen I know takes -3. Crisscross those. I'm just going to write them here. Yes, remember those are the preferred charges. Crisscross them. You get Ca3N2, calcium nitride. And if you want to balance this, all you need to do is throw a 3 here. You've already got 2 nitrogens on both sides. You just need 3 calciums on both sides. And that's it. So synthesis reactions are pretty simple, straightforward. You take two things, put them together to make a new thing. With ionic compounds, we just did this the entire time last week. We took our ionic compounds, had their preferred charges, and we made their compounds. So you should be expected to be given reactants. You should be expected for a synthesis reaction to be able to make the ionic compound that would result from combining the elements in question. All right, so it's just charge balancing. That's all it is. Anything else about these? Oh, I should mention there are 7 elements. I don't know how to spell occur. Okuru. Nope, let's try again. Occur as pairs. These are called diatomic elements. That's why you see, for example, I have Cl2 and N2, and we had O2 before and H2. There are 7 elements that always occur in nature as pairs. They never occur as single atoms. And so these are the elements that occur as pairs, that are called diatomic elements. They always occur as pairs. So you'll never find one H atom by itself. You'll always see H2. One way to remember this is Hofbrinkel. As I have written there, Hofbrinkel. That's how I learned it, at least. You can also, understand it's all of the halogens plus hydrogen, oxygen, nitrogen. If there's some way for you to remember that. There's plenty of mnemonics online I'm sure you could find as well. So you'll want to know that in chemical reactions, these elements always occur if they're by themselves like this. Sodium, calcium, whatever, those just can be by themselves. That's not a problem. But if you are ever dealing with one of these 7 elements by themselves, they should have the 2 on them. So that's why we see here we have Cl2, because chlorine by itself is always Cl2. Nitrogen by itself is N2. Same thing with hydrogen. Same thing with oxygen up there. So when these elements are by themselves, they will occur as diatomic. Okay, but that's just something else to learn. All right, let's look at the opposite reaction. Let's look at what's called decomposition. Decomposition reactions are the opposite. They are one thing turning into multiple things, breaking down. We saw this with the hydrogen peroxide breaking into oxygen and water. Another common one would be this. Taking calcium carbonate, breaking it into calcium oxide and carbon dioxide. This is a very common pattern for decomposition if you throw some heat on these things. Delta means heat, by the way. Oftentimes you'll need to heat these reactions. This is very common. You'll have some sort of metal carbonate will decompose with heat into the metal oxide plus CO2. So this is one you're going to be expected to predict the products of. If I tell you I'm heating calcium carbonate, you're going to give me calcium oxide and CO2 out. We can look at another one. They're not too bad. If we say we have magnesium carbonate, we will heat that. That should just give us magnesium oxide plus CO2. And it works out because carbonate and oxide have the same charges, so nothing really changes. Like whatever subscript you have with magnesium, that stays. Whatever subscript you have with carbonate becomes the subscript for oxygen. So say if you had something like this. If you were to heat this guy, you're going to break it into the metal oxide. And you're going to, in this case, have 3 carbon dioxides because you have 3 carbonates to begin with. So it's just a simple thing. Nothing, charges don't change. So cobalt was 3 plus on the left. It's going to be 3 plus on the right. These are pretty straightforward. So that's one kind of common decomposition reaction. Another one that we'll want to learn is this one. You can decompose oxides as well if you heat them up. If you take a metal oxide, that will turn into your metal plus oxygen gas, O2. So straightforward, just split them up. Throw a 2 on the oxygen. For example, silver oxide, You can do this with silver oxide. If you heat it up, you'll get silver plus oxygen out. Predicting the products isn't bad. If you wanted to balance things, which you should probably do, for example, we needed to balance the mercuries there because we have oxygen as O2. We're going to see with this next one, we would end up with 2 of these and 4 of those if we were to balance this. So those ones aren't too hard to balance because there's just 2 elements. Those usually are pretty easy. So those are kind of the 2 patterns for decomposition that I would expect you to know. So a metal carbonate breaking down into the oxide and CO2, and then a metal oxide breaking down into the metal and oxygen gas. So those are kind of 2 reactions so far. The last one is the easiest to predict the products for. The last reaction type is combustion. And that follows this pattern. You'll always make CO2 and H2O. It doesn't matter what your coefficients for carbon, hydrogen, oxygen are in your molecule. These all turn into CO2 and water. So if we saw a couple of examples, we saw propane and butane burning, combusting. We produce CO2 and water for both of those. Oftentimes, I've put a Z for oxygen. That can be 0. So you could just have CXHY. And whatever, that's just a hydrocarbon. But sometimes you have oxygen with these as well. And these always have the same pattern. So you're always going to make CO2 and H2O. So if I ask you to predict the products of a combustion reaction, it's CO2 and H2O. It's always this pattern here. So, for example, if we burn glucose, we make CO2 and water. If we burn hexane, we get CO2 and water. If we take methanol and burn it, guess what? We get CO2 and water. If we take C2014 H4000, we get CO2 and water. So, and we can balance these. Do you want to balance the last one? It's actually not that bad. It's just going to have really big numbers, but it's really not that bad. But combustion reactions are very easy to identify and then figure out what the products are. You'll have some combination of carbon, hydrogen, and oxygen. Again, oxygen is optional. Add O2, produce CO2 and water. And so, pretty simple pattern there. Alright, any questions on these types of reactions? So with these, you will be expected to do the things kind of in blue here. So I want you to be able to predict the product of a combination reaction that involves a metal and a nonmetal. You'll make the ionic compound that's formed. You'll remember that there are 7 diatomic elements. For decomposition, I want you to know 2 patterns. Metal carbonates decomposing as well as metal oxides decomposing. They follow patterns. Metal carbonates turn into the corresponding oxides and carbon dioxide. And metal oxides would turn into the metal and oxygen gas. Alright, and then combustion reactions always produce CO2 and water. So those are kind of the types of reactions we're looking at there. All right. Cool then. Let's talk about what to do with these reactions now that we're talking about them. With these, some important things that we're going to talk about are, let's say that, Miss Jersey, relax. Let's take our nitrogen and hydrogen combination to make ammonia. If you look at this reaction, this is a very, very important industrial reaction. This is being done, tons and tons and tons of ammonia are being made through this process, through this reaction. And it's one we're going to study at length in C111 or 113 if you take that class. You'll love this reaction. Regardless, this is essentially a recipe. It tells us that we need 1 molecule of nitrogen, 3 molecules of hydrogen will give us 2 molecules of ammonia. That's what these coefficients mean. So this is how it might be kind of described atomically. We have our nitrogen, we have our hydrogens, we put them together, we've made 2 ammonias, with the nitrogens being blue and the hydrogens being purple there. And so that's what it looks like. So this recipe tells us that in order to make 2 molecules of ammonia, we need 1 molecule of N2 and 3 molecules of H2. It's a recipe. And one important thing about recipes, that we know, is we can scale them up. 2 ammonia molecules, that's all well and good, but that's not very many. Ammonia is not a huge molecule. We can't really use 1 molecule of it. We need, I don't know, let's say I want 10 to the 25th molecules. That's a reasonable amount. It's actually not that much. I want 10 to the 25th power molecules of ammonia. This recipe tells us how many of nitrogen and how many of hydrogen we're going to need. If I want 10 to the 25th molecules of ammonia, that means I need to put in half of that, whatever number that happens to be, 10 to the 25th divided by 2, so fine, I'll even say it, 5 times 10 to the 24th. That's half of 10 to the 25th. And I'm going to need a little bit more. I'm going to need, in fact, 1.5 times 10 to the 25th power of hydrogen. Right? If I want 1 times that much, I have to put in 3 over 2 hydrogens per ammonia, right? I need 3 hydrogens to make 2 ammonias. So if I want to make 1 times 10 to the 25th power, I need 50% more hydrogens than that. So I need a little bit more. But this is crazy. How the hell am I going to count out 5 times 10 to the 24 molecules of nitrogen, or 1.5 times 10 to the 25th of hydrogen? It's absurd. But we have a way to do this. Right? If we are doing our baking of a cake or whatever, Very often we'll mass out the ingredients. We'll say, okay, well, for this pound cake, I need a pound of flour, a pound of sugar, a pound of butter, a pound of eggs, right? I need masses of these. Masses are easy to measure. I can't count out grains of flour or grains of sugar. Nobody's going to put that on the recipe, right? It's absurd to think of that. So, but something we can do in the lab is mass. And it turns out that we have defined a unit to kind of bring things from molecular land, where we're talking about individual molecules, to mass. And that unit is called the mole. And it used to be defined as, it's slightly different now, but it was the specific number of carbon-12 atoms that weighed exactly 12 grams. This is what a mole was defined of. It's that number of carbon-12 atoms that will weigh 12 grams. And so this brings us then from atomic level to grams, something we can measure. 12 grams is, 2 teaspoons or so of carbon-12, I would say, of charcoal. That's about how much we're talking about. And this happens to be this magic number was that's repeating all those zeros. It's exactly 12. So I'm just going to put 12. So it turns out that this magic number, which we call Avogadro's number after the scientists, that number of atoms of carbon-12 is equal to 12 grams. So, using some fancy calculations. Often, though, we don't actually use this number. It's kind of a little bit crazy, right? So what we say is 1 mole of carbon-12 equals 12 grams. And that's a little bit easier. So 1 mole is essentially just a substitute for this number. It is going to avoid crazy big exponents, and it's going to help us kind of see things a little bit more clearly. So you see these 10 to the 23rd power of atoms? That's a huge number, right? How the heck would we ever count those? So if I needed 10 to the 25th power of ammonias, that's not really that far off. And we can figure out what mass that's going to be. And we can therefore find out the masses of the ammonia and hydrogen that we're going to need based on our thing here. We're going to see that we can kind of expand this idea from 1 mole of anything is going to be equal to what's called the molar mass in grams. And the molar mass, since carbon-12 is special, that it would weigh 12 grams, we're going to see that this is going to be the kind of the sum of your atomic masses in your compound that you're looking at. Let's take a look at this. What the heck is molar mass? Well, we know that each water molecule has 2 hydrogens, 1 oxygen. So the molar mass would be just adding those up. So 2 times the mass of hydrogen plus 1 times the mass of oxygen. If we go ahead and look those up on the periodic table, those numbers are from the periodic table. I have them memorized because I've used these so many times. These are atomic masses. These are the numbers that are underneath your element. You'll have your atomic number on top, atomic mass on the bottom. Those are from the periodic table. And if we add those up, we get 18.02, I'm going to say. I don't really worry about sig figs with molar mass because we're going to see that different periodic tables give you different numbers of sig figs. So I usually just leave it, just go ahead and round to 2 decimal places because whatever periodic table you're going to be using may give you slightly different atomic masses. Just depends on how many sig figs they give you. So if we add this up, we get 18.02. And what is important about that number is it tells us that 1 mole of water is equal to 18.02 grams water. Or if you were truly crazy, which we probably are because that's why you're taking chemistry, right? We could also say that many molecules, Avogadro's number of molecules would be equal to 18.02 grams of water. So remember, a mole and Avogadro's number mean the same thing. But which of these is easier to use as a conversion factor? Hopefully we can see it's the top one, right? The bottom one, again, we're going to be dealing with all these crazy exponents. It's really quite silly. And so instead of talking about 10 to the 25th power of nitrogen molecules, or ammonia molecules rather, I think that's what I wanted, we can see that I could make this into moles if I wanted by dividing by Avogadro's number. 1 mole is equal to 6.022 times 10 to the 23rd of whatever you're looking at, molecules, atoms, whatever. Moles and molecules are not the same, by the way. I know they look the same. They both have mole in them, right? Moles and molecules are not the same thing. 1 mole of molecules is 6.022 times 10 to the 23rd molecules. A mole is just a word like dozen. Like a dozen means 12, right? A mole means 6.022 times 10 to the 23rd. It's the same thing as a dozen, but just a different number. So, or if you're Abraham Lincoln and saying 7 years ago, that's 87, right? Because 1 score is 20. So, same thing. A mole is just a really big number. We could say, instead of this pesky amount of molecules, I'm going to actually move it a little bit to the left. If I wanted to see how many moles that is, let's pretend that says molecules. Well, we can just say, okay, well, I know that 1 mole of ammonia is the same thing as that many molecules. And we're going to see this will be a little bit easier to work with. So let me go ahead and, I don't even have a calculator in my closet here. So 10 to the 25 divided by 6.022 times 10 to the 23rd power. Let's hope this works out. Why are you giving me images, Google? There we go. I get 16.6 moles. And so if someone were to come up to you and say, I need 10 to the 25th power of these, or someone were to come up to you and say, I want 16.6 of these, a little bit easier to conceptualize the 16.6, right? Because who wants all these crazy molecules? Not so easy. I don't know if I just heard the doorbell. I hope the movers aren't early. Well, we'll see. With this, we can do all sorts of fun stuff. If we wanted, I'm going to rewrite our reaction here. If we wanted 16.6 moles of ammonia, we're going to see that these coefficients in this reaction are conversion factors. We could say, okay, if we're going to make 2 molecules of ammonia, or 2 moles of ammonia, I need 3 hydrogens to go in there. Right? Think about it, if we have our lovely diagrams or little molecules here. I need 3 hydrogen molecules. I get out 2 ammonia molecules. So that's essentially equal to each other for this reaction. And so I could also say, well, 2 dozen ammonias. Well, I would need 3 dozen hydrogens to make that. Or I could say 2 moles of ammonia and 3 moles hydrogen. And so this is going to be a little bit easier for us because now we have conversion factors that are going to be very useful to us. If we saw that I wanted 16.6 moles of ammonia, we can see how much hydrogen I would need by using this relationship, using the coefficients from our reaction. We can say, okay, 16.6 moles of ammonia, just like any other unit conversion, we can use this as a conversion factor. We're going to see we can put 2 moles of ammonia on the bottom, 3 moles of H2 on top, and this is going to be how many moles of hydrogen we need to put in. So 16.6 times 1.5 gives us 24.9 moles of hydrogen. And I get it. What the heck? How the hell am I going to measure 24.9 moles of hydrogen? Well, we have the other conversion factor. Remember, the definition of the mole tells us that 1 mole is equal to the mass, the molar mass of your compound. If we think the molar mass of hydrogen would just be 2 times hydrogen, which is 2 times 1.008, which is 2.016. We have another conversion factor. 1 mole of hydrogen equals 2.016 grams hydrogen. The molar mass. And so now we can say, okay, well, I've got this number of moles now. I can actually now turn that into something useful. I can say, oh, I can actually measure out the grams. I have a balance. I can do this. Yes, we can do it. We can say 24.9 moles of hydrogen. Again, moles of hydrogen is going to go on the bottom because we need those to cancel out. Our calculated molar mass goes on top. And we end up with, let's go ahead and do it, times 2.016. We need 50 point, well, let's say 50.2. I'm not really worried about the sig figs here because I gave you just something with 0 sig figs, but I'm not worried about that. I only need 50 grams of hydrogen to make my 10 to the 25th power molecules of ammonia. Isn't that crazy? 50 grams. That's not very much. Consider a shot glass full of water. That weighs about 45 grams. Just the water. Not very much, right? 1.5 ounces of water. Not even a quarter cup. That mass, that same weight of hydrogen is all I need to make 10 to the 25th power molecules of ammonia. So I told you 10 to the 25th power molecules of ammonia is not very much. I wasn't lying. It's not very much. It may seem like it. It is indeed a huge number, but in reality, it's not very much mass. We're going to be dealing with far, far greater exponents in the industry. So, okay, so I do need to actually end here because I hear the mover's truck downstairs is beeping. So what I do want you to do, though, is there is kind of one bit that I just covered this morning in 101 on empirical formula. I'm going to just have y'all watch that video because it's the same thing I would have to do next time. It'll just save that bit of time there. So that's going to be kind of one more little bit here. So you're also going to watch the video for C111 today, which is, it'll be on there. It's on empirical formula. And it's using this idea of moles. It's how we can take experimental data and determine the formula of a compound using the mole idea. So we're going to pick up with this on... So this is from this morning's video. So it'll be on Twitch today. I'll put the title up. These will be on YouTube later than normal today. Just again, because I have to deal with the movers. And so, yeah, we'll go from there. So Thursday, we'll pick up with more of these reactions idea. We'll see how to kind of set up an entire thing where we're going from our kind of reactants to our products, finding out how much reactant we need to make a certain amount of product, or given a certain amount of reactant, how much product we could get out. We'll go with that. But for this idea of the empirical formula, I'm going to just have you watch the video I did this morning because it's the same thing. So we'll go for there. Okay. I'll put in Discord that things are going to just be up a little bit later than normal today, just due to the craziness. So I beg your patience. With that, I'll see you on Thursday, so enjoy the rest of your day. We'll continue on. As always, post questions in Discord if you have any that come up. And take care. We'll see you on Thursday.